All right, so thus begins what is effectively week 2 of summer circuits. This is July 2nd, so we're making it through. Today, what we will do is continue what we were working on yesterday in terms of introducing some of these resistive circuits, continue looking at KCL and KVL, and then start looking at voltage and current division, which will form the foundation for a lot of what we'll do going forward. So in the way of announcements, I think that I've gotten one online submission of Quiz Zero, and I think about half of the in-class students have done that. So make sure that you,
Where is that? Is that on WebCT?
Quiz Zero was just come by my office.
Oh.
Yeah.
Okay.
So stop by my office or send me an email. If you're an off-campus student, it doesn't make a lot of sense to make you drive all the way up here and say hi. So send me an email or an IM conversation or whatever. I did post a homework assignment yesterday, a midday kind of time frame, with a to be determined due date. It depends on when we finish it, but I think that we'll get through enough of the material today for you to get a good start on it. The likelihood is that we'd be shooting for something in the neighborhood of a Monday due date. So figure out how you do that. Also, online students, I need to see some more proctor forms because I think I've gotten 2 so far. So the last thing is that I'm pretty sure we're going to shoot to do a quiz at the end of class tomorrow. Online students, again, you'll have a certain a certain period of time after the class is actually finished recording to do that. Instructions will be posted on WebCT when the time comes. Any questions? All right, so let's review the stuff that we talked about yesterday on resistive circuits. So we started talking about Ohm's law. We talked about Kirchhoff's current law, Kirchhoff's voltage law. So what were those things? Resistance, again, is the basic concept that electric current doesn't flow nicely, and we can quantify the degree to which the electrical flow is resisted by the conductor itself or by an element within the circuit. Devices whose sole purpose in life is to provide resistance are called resistors. It's measured in ohms, and the unit abbreviation is that capital omega. The current voltage relationship is given by Ohm's law, which is that symbol, excuse me, V equals IR. So the voltage across an element is proportional to the resistance and the current going through it. An ohm then is technically defined as a volt per amp, for what it's worth. The resistance of relating resistance to power, then, we can take our power equation from lecture 1, P equals VI, and substitute in Ohm's law, V equals IR, which gives us 2 new forms of the equation. Power equals I squared times R, or the current squared times the resistance, and it also equals V squared over R. The important takeaways here, again, are listed on the bottom of the slide. The first is that power is nonlinear. So the more voltage you apply, the more current you apply, it goes up quadratically in terms of the amount of power that's consumed by the device. The second thing is that in a purely resistive element, there is no chance at all for power to be supplied to the circuit, because the passive sign convention says if you're going to supply power to the circuit, you need to be able to have a negative sign on your power. The I squared and the V squared both make sure that that can never happen. You're always going to end up with a positive power. Passive sign convention says that is a power that is absorbed by the element. We can also talk about conductance. I don't find it to be particularly useful, but it is the reciprocal of resistance measured in Siemens. Capital S is the unit. And you can rewrite all of the current voltage relationships, the power relationships in terms of conductance. So the current equals the conductance times the voltage. That's just the restatement of Ohm's law. And then we can restate both of the power equations, I squared over G and G times V squared. You can use those as you see fit, but like I said yesterday, I don't find them to be particularly useful. 2 important resistances we talked about, the short circuit. Where there is zero resistance, if you plug that into Ohm's law, what that tells you is that there's no voltage across there. With a zero resistance, it gives you zero voltage. That doesn't mean that that current can't necessarily flow. It just means that there's not going to be any voltage in that part of the circuit. An open circuit is where the resistance is infinite. Again, plug that into Ohm's law, and the voltage divided by the resistance, which should give us the current, shows us that anything over infinity is zero, and so there's no current that flows through an open circuit. And that kind of is intuitively makes sense. You have a wire over here, you have a wire over here, and they don't connect, and so no current is flowing between them. We looked at a few simple examples of power and resistance, and then we started talking about Kirchhoff's law, or his two laws. He came up with these when he was a student, and they form the basis for an awful lot of what we do in this class. We talked about some definitions that we need to get through it. A node is a connection between two circuit elements. A loop is a closed path where you only encounter a given node once, and you can see in a complex circuit there can be lots of loops. There might only be one loop. And we'll start off with simple single loop circuits. And a branch is a circuit element plus the two nodes on either end. So that allows us to get to these laws, the first of which is Kirchhoff's current law. It says that the algebraic sum of all the currents entering a node is zero. And I think what a more intuitive way of interpreting that is to say that all of the currents entering a node have to equal the sum of the currents leaving the node. And the convention that we work with, and it doesn't matter exactly, if you want to flip it the other way, that's fine. But the convention that we work with is that if the current is entering a node, we're going to give it a negative sign. And if the current is leaving the node, then we're going to give it a positive sign. And that allows us to make this summation work. And then it should all sum up to zero. Kirchhoff's voltage law is the same kind of thing. It says going around any closed loop, the sum of the voltages should equal zero. And the way that we'll make that work is we just pay attention to what is the polarity of what is the voltage terminal that we enter first as we're going around the loop. And so whichever one that is, that's the sign of that term in the KVL equation. And we looked at a couple of examples of that, and that brings us up to where we are at now. So we've got one example that I want you guys to try real quick, very simple kind of thing. But here is a circuit, a very simple kind of guy. Okay, I think that's everything you need. We got a 24 volt source. We've got 3 resistors with marked voltages across them. We've got, I guess, four resistors, and then we've got this extra 6 volt source. So using KVL, find VAD and VEB. So take a couple minutes. Watch the clock, just write those equations out, and we'll come back in just a minute. All right. So writing these again, it's just as simple as walking your way around the loop and summing up the voltages with the terminals as you run into them. So we run into the 24 volt source. We start a day, we run into the 24 volt source first. It's got a positive sign that we run into that terminal of the voltage source first, so it's going to be a plus 24. We run into the negative 4 volts of the resistor, positive 6 of the source, and that's it. We've gotten from node A to node D, so that should give us 26. And voltage EB, same kind of thing. We run into the negative 8, we run into a negative 6. See how far we're going here, and then a positive 24. So that's a negative 14 and a positive 24 should give us positive 10. That should have gotten us all the way around. So just some simple examples, and it gets somewhat more complicated as we start going around more complicated loops. And when we're not given things like what is that voltage across the resistor. And I think that's actually what we move into exactly right now, is what if we don't know those kinds of things? So we can have these things, these single loop circuits, just has some sort of voltage source or whatever, and maybe we have a couple of resistors hanging out here. And what we know is that there's some sort of voltage coming out of the source, consequently, and because there is some sort of resistance in the circuit, there is going to be current flowing, some sort of current I, and we've got two resistors that have some kind of resistance, whatever they happen to be. Correspondingly, there's going to be some voltage across each one of these. Should be R2. And what we know is KCL says that because these are part of the same loop, and because essentially, the slide says, KCL says that the current through all of the elements in a single loop circuit are the same. And here, and that might say, you say, how does that come out of KCL? Well, here's a node, here, let's see, here is a node, and here is a node. So the current entering a given node has to equal the current leaving the node, right? Well, it comes up to here. Where else can it go except through here, and then through that resistor? It gets to this node. Where else can it go? It has to keep, it goes through the next resistor. And so that gives us the rationale for why the current around a given loop is the same. It doesn't have anywhere else to go. So the same current is going to be flowing through both of these resistors, but what about the voltage across each one of those resistors? That may or may not be the same, and it depends pretty much entirely on the values of the resistances themselves. So on the slide there's some nice math that kind of tells us what's going on here. If we write the KCL equation, or it's actually a KVL equation around this loop, we run into the negative terminal of the voltage source first, if we're going around clockwise. We run into the negative terminal of the voltage source first, then we run into the positive terminal of our first resistor, the positive terminal of our second resistor, and that closes the loop. KVL says that equals 0. And so we can simplify that, move around the terms, and just push that voltage source onto the other side. So what that tells us is that whatever voltage is being created by the source, those is going to be divided in some way across those two resistors. But in what way, that we need to still figure out. So if we recall that the voltage across any one of those resistors would be given as the current running through the resistor times the resistance itself, then that gives us, we can substitute both of those things back into our first equation from the first bullet. So we stick in R1 times I of t and R2 times I of t, and we simplify the equation a little bit, pull out that common I of t term, and then divide both sides by the R1 plus R2. And let's take a look at the math on that real quick, just so it makes sense. So we had V of t equals VR1 plus VR2. And we knew from Ohm's law that this should be R1 times I of t plus R2 times I of t, because KCL told us it's the same current. So we factor out the I of t term, and we're left with R1 plus R2. Divide both sides by V of t, or by the R1 plus R2 term. We get R1 plus R2 equals the current. And so now if we know the voltage that we have and that's coming out of the source, and we know the resistance values, we can solve for what the current is, and then we can go back and solve for the voltages across each one of the resistors. So that's one way of dealing with it, and it gives us something. Then we can also take and go back. If we can take a look at the slide again, what we do then is take the equation that we came up with for I of t, and substitute that back into each one of the two voltage equations down at the bottom. And so what you see is that there is going to be some proportion of the current, of the voltage, that's divided across each of the two resistors. And what is kind of the way to remember this when you're trying to do a voltage division across two resistors is we take the resistor that we're interested in, and so on the first one, we're looking at VR1. We want VR1, so we put R1 on top, we put the sum of the two resistors on the bottom, multiply that by the source voltage. Same thing on the bottom. R2 is the one that we're interested in. We put R2 on the top, we put the sum of them on the bottom, multiply that by the voltage, and that gives us the proportion of the voltage that's across each one of those resistors, and that's called voltage division. That's what it's most commonly referred to as. So we can do I think there's at least one good example in my notes here on voltage division. So let's use that to make something happen. So here we've got a single loop circuit. It's got two resistors in them, or in it, I suppose. Two resistors, single loop circuit. We know that the source voltage is 9 volts, and we know that we have 90 kiloohms across in the first resistor, and we've got 30 kiloohms in the second resistor. And so let's call this one R1 and this one R2, so that we can you can look back at your notes and consider the equations, that the voltage across R1 is going to be given as R1 over R1 plus R2 times the source voltage. And we used V of t in the original equation. In this case, that'll be the 9 volts. So let's plug in the numbers. We've got 90 kiloohms over 120 kiloohms. And we multiply that by the 9 volts. And we've got VR2, which is going to be R2 over the sum of the resistances, R1 plus R2. Multiply that by that source voltage. And so that's going to be 30 over 120 times 9. Let's see, 9 over 12 times 9. So we've got 6 3/4 volts across the 90 kiloohm resistor, and we've got divided by 12. We've got 2 1/4 across the second resistor, the 30 kiloohm resistor. So there's at least, and for what it's worth, if we want to, we can go ahead and we can find out what that current actually was as well if we wanted to, because now we know what the voltage is across each one of those resistors, and so we should solve for it. Let's just for kind of kicks, let's solve for it from both of those. So we say the current that's running through resistor 1, we'll call it I1, equals the voltage across it, VR1, 6.75, divided by the resistance of the 90 kiloohms. 6.75 divided by 90 is a very small number. It's, I guess that's 0.075 milliamps. And we can solve for the other one too. That should be the voltage 2.25 over the 30 kiloohms. And that should give us the same answer, or else we screwed something up. And we do get 0.075 milliamps. So that's voltage division, and that's about as hard as it gets. Now, I think in the textbook it does give you some more information on how to do this with larger numbers of resistors than just 2, but I have always found that if I try to do that, I will screw it up. Pretty much 100% of the time I will screw it up. And we'll look at techniques later in this chapter on how to combine resistors so that we can get it down to this kind of simple 2-resistor setup. And you can do the simple voltage division and usually get it right, as opposed to usually get it wrong. So that would be my advice to you on that one. So, all right. So here's another deal that we want to take a look at real quick, which is how to deal with multiple sources and multiple resistors. And the first thing that we look at in these single loop circuits is how do we deal with multiple voltage sources so that we can apply our KVL equations. So let's consider that we have, and this is a very goofy and contrived circuit to be sure, but we have a resistor. We've got a whole bunch of sources. And I don't know why you would do this, but it's kind of like randomly sticking a bunch of batteries into a circuit. But hey, it's a good academic example, right? So we've got some R1 here, we've got some V2 here, V3 here, R2 here, V4 here, this is V5, and we finally get back around to V1. And so if we want to, and it frequently makes our analysis a whole heck of a lot easier to do this, is that we can just combine all of these various voltage sources into a single voltage source. And as long as the voltage sources are in series, you can do that. As soon as you start seeing voltage sources in parallel, you got to knock it off because you can't do it. They have to be in series for you to be able to do this. And then we just sum them up in the same way that maybe you were writing a KVL equation around the loop. And so let's start and say, well, let's call the V combined what we're going to reduce this down to in terms of a single source. And we just start walking our way around each one of the loops. And this, it looks like there's a typo on the slides as well as in my notes, but because we're supposed to just algebraically sum the sources, but each one of the signs is a little backwards from what I would expect, and it shouldn't matter as long as you do it properly. So, but I will follow my notes so that it makes sense. I don't like that though. Let's do it the way that makes more intuitive sense. We run into the negative terminal of V1 first, so negative V1. We run into the positive terminal of V2. We run into the negative terminal of V3. We run into the positive terminal of V4. And we run into the positive terminal of V5. So algebraically combine all of those values and it will give you a single voltage source. And so you could reduce that down and turn it into a single source. And we'll do some examples with real numbers here in a little bit. But all you have to do, just walk around and make sure that as you run into the sources, take the appropriate terminals and add them up appropriately, and so then you can reduce this down to a single source. And you'll have to pay attention. Kind of the assumption is that it will look like this, but if you get a negative voltage out of this equation, those terminals will have to switch around. But that gives us something where we just have two resistors and a single source. This is the source VCOM, and it's R1, that's R2. And it doesn't matter that we have sources intermixed with the resistors. We can still deal with it, not a big deal. So that's actually slide 4. Okay. So then the next one is, how do we combine multiple resistors into a single resistor? And let's take a look at another very contrived circuit. So here is something, and we have a whole bunch of resistors. And this is a really big and very odd circuit, but we end up having a total of n resistors in this circuit. So this is R1, R2, R3, R4, R5, and so on until we get to Rn. So we've got n resistors in this circuit. And we've got some sort of voltage source across here, and then each one of these has an associated voltage drop across it of VR1, VR2, and so on and so forth, up to VRN. So KVL going around this, because of the polarities of each of the voltages of the resistors and whatnot, says that eventually what it will tell you is that the voltage that comes out of the source is going to be equal to the voltage drops across each one of the resistors. So VR1 plus VR2 plus VR3, and so on up to VRN. If we apply Ohm's law to that to figure out what is the voltage, each one of those voltages, you get I of t, whatever that happens to be in the circuit, times R1 plus I of t times R2 plus I of t times R3, and so on out to I of t times Rn, because all of them have the same current rolling through them. Factor out the I of t part, and so we get I of t times R1 plus R2 plus R3 all the way out to Rn. And what this kind of tells us is that we could replace all of those resistors, all of those series resistors, with a single resistance of the value of the sum of all of those resistances, and we would see the same behavior out of the circuit, and that's the important kind of thing. So if we can replace all the resistors with a single RS such that RS equals R1 plus R2 plus R3 plus Rn. So, and at this point, it's probably worth discussing exactly what makes something series versus parallel, just in case it's not clear. When we see, if we were to start laying out all of the nodes in this circuit, elements that are in series have only one node in common, and that's the node that connects them. So these two things happen to be in series because, let's call this node 1, node 2, node 3, because of the three nodes that are in those two circuit elements, those two branches of the circuit, right? The only one that they share is node 2. And there are no other things coming off them, so these two things are in series. Things that are in series have the same current running through them. So just for what that's worth as well. So we can do those two things. So now we can combine the voltage sources, and we can also combine the resistors to get it down to something that makes sense for us. So here's an example of putting all these things together. We've got a 6-volt source, we've got 10K resistor, we've got a 20K resistor, we have a 12-volt source, and we've got one more resistor down here on the bottom. This is a 12-volt source, and we have a 10K resistor, we've got a 20K resistor, and down here we have a 30K resistor. So the things that we want to find I, which is just the current that's going to be running around in this circuit. We want to find, let's see, we need to label all these, A time B, C, D, and E. We want to find the voltage BD, so the voltage across the 20K resistor as well as including the 12-volt source. And let's see, the power that's in the 30K resistor. And we also want to find VBC, or which is the voltage across the 20K resistor. So those are all of the things that we want to find when we're trying to do this. And I don't like that so the first thing that we need to do is use the concepts that we've learned to figure out what to drop this down to something where we can start using voltage division and stuff to figure out what's going on. The first thing is to combine the two voltage sources. We say, well, the new, say, V sub S is going to be the -6 plus the 12, and what you get out of this is a 6. And so what that kind of tells you is that the polarity of these two voltages, or the combined voltage, when we're going around the loop clockwise, the way that we keep doing this, we keep going around clockwise, that we need to hit the positive terminal first when we make the reduced version of this circuit. So what we're going to have is a 6 volts that are coming out of the source, but again, we have a positive sign on that voltage, and so that tells us that we need to run into the positive sign of the voltage source first. And that's opposite from this, but it has to do with the greater magnitude of this other source on the right-hand side of the circuit. And then, we can reduce this as much as we want to start figuring out what's going on. And what I would almost encourage you to do to start with is to reduce this down to the smallest possible circuit. And the smallest possible circuit would be one voltage source and one resistor. And so that would be 10 plus 20 plus 30, so we'd have a single 60K resistor over here. So the current, there's the 6 volts across this source have to be the same 6 volts that are across this resistor. And what is tremendously important about this is that we've reduced this circuit down to this circuit, but what has not changed yet is that it's the same current. This current I and this current I are going to be exactly the same. So we've got, and now here's where this may look a little confusing and a little arbitrary, but this is where convention kind of comes in, that we defined I as running around the circuit clockwise, but that kind of ends up screwing up our passive sign convention, because that's going to end up if we got a positive current, that's going to end up causing this to turn into a an element that absorbs power from the circuit, and that's generally bad. We don't want to, that's not usually going to happen. So what will realistically happen is that the positive terminal down here is going to be down here, and the negative terminal is going to be up there for that resistor. And if we solve for things like this, we should end up getting a negative current somewhere along the lines, or else the circuit's not going to behave in a normal fashion. The voltage across the resistor is proportional to the current times the resistance. We know that there's got to be 6 volts across it, but let's right now sit down and say this is going to be a negative voltage that's across it, or else either you can look at it that way, or you can say I need to switch the currents around to make sure that the current is running through here and coming into the positive node of this resistor. Any way you want to think about it, that's going to be the important thing. But we've got to solve for what the current is, that's going to be the voltage over the resistance. Say the magnitude of I is going to be equal to the 6 volts divided by the 60 kiloohms, which gives us a 10 milliamp current, or 0.10 milliamp current. And because of the polarity of the voltage source, this has to be a negative to give us what is the right current. And that way, if we've defined I as going clockwise, it's not actually going clockwise. It's going counterclockwise in the circuit because of the polarity of the voltage source and whatnot. So this current I is the negative 0.1 milliamps. This current I is the same 0.1 milliamps. And it ends up being that negative value because of the polarity of the voltage sources, and it's really going around the other way. So that's I. We found what I is. It's negative 0.1 milliamps. And again, it's the passive sign convention that we're trying to obey that gives us the negative sign on it. VBD. So we want to find the voltage between node B and node D. And again, to make sure that, so if we were to go ahead and say, all right, let's make these plus minus, plus minus, plus minus in the original circuit, and that's probably fine given that we've defined I as running around clockwise, and so we want to make sure that we're obeying the passive sign convention and that the current is going in here. And so we just need to make sure that we remember that, well, this is a negative current. So the voltage from B to D is going to be equal to the voltage across the 20K resistor plus the voltage of the 12 volt source, which is 12 volts, because we ran into the positive terminal first. What is the voltage across the 20K resistor? Well, it's 20 kiloohms times the current that's running through it, which is the negative 0.1 milliamps. And we add on the 12 volts from the source. 20 to the third times 0.1 to the negative third gives us negative 2 plus 10 equals 12 equals 10 volts. And that's the voltage across from B to D. We want to know what the power is that's in the 30K resistor. And so we can use a couple of different ways to do that. We can do I squared R, we can do V squared over R. At this point, we don't happen to know what the voltage is. We haven't solved for the voltage. We could. We know what the current is. We know what the resistance is. So we could solve for the voltage. But why? We don't need to. We have a way to solve this without knowing the voltage, right? The power in the 30K resistor equals the current that's running through it, I squared, times the resistance, 30K. That current is that negative 0.1 milliamps squared times the 30 kiloohms. So negative 0.1 e negative 3 squared times 33 gives us a fairly small amount of power. And that, yeah, okay, that's right. So it's 0.0003 watts, and that's the same as 0.3 milliwatts. One thing I've always been really terrible about is putting in the leading zeros on those kinds of numbers. I've always hated doing it, and I just always drop it. So that was the power in the 30K resistor. One more thing that we need to figure out is what is the voltage across BC, or what is the voltage across the 20K resistor. Easiest way to do that is the voltage across the 20K resistor equals the current that's running through it times the 20 kiloohms. Why work any harder? I don't know why I have, in my notes for some reason, I have the power that's absorbed by the 20K resistor, and I have no idea why I would do that. But anyways, there's that negative 0.1 milliamps that are running through it times the 20 kiloohms of resistance. So that's negative 0.1 e negative 3 times 23, or negative 2 volts. And we already kind of figured that out back up here, right? That's the same equation as up here. So you could, and in the example as it's worked out in the book, does the same kind of thing, but they drop it down to 2 resistors, and I think that makes it a little bit more difficult, but you can do a voltage division across the resistances if you want. I don't think that's particularly useful. So, any questions on voltage division? You guys want to try an example or anything, or does that make a lot of sense? Kind of the key thing again to remember is that when you're doing the voltage division, you need to have 2 series resistors. As long as you have that and you have a single voltage source, take the resistance that you're interested in, put that on the top of a fraction. In the denominator, you're going to put the sum of the resistances, of the 2 resistances, and multiply that by the source voltage, and that will give you the proportion of the source voltage that is across that particular resistor. The larger the resistor, relative to its neighbor, the greater amount of voltage that's going to be across it. So that should kind of intuitively make some amount of sense too. So let's look at single node pair circuits now. These are similar kinds of simple circuits that get us going on what we're looking for. So in this case, what we're going to do is we're going to change our circuit a little bit such that instead of having a single loop, we have essentially we've got 2 loops now. And they're called in the book single node pair circuits because realistically there is a single pair of nodes that makes up the circuit. We have 3 branches, but we only have 2 nodes in the entire circuit. We've got some sort of current I of t, and we've got these 2 resistors, R1 and R2, and this current IT has to split between these 2 branches. And there's 2 things that are worth noting. The first is that KVL says that the voltage across this has to be the voltage across this, and it's going to be the same as the voltage across this, because the voltage around any closed loop is supposed to equal 0, right? That's what KVL says. So whatever voltage is across the current source has to be across R1, because in that closed loop, that has to equal 0. Then in this closed loop, well, that also has to be the same. And so all 3 of these elements have the same voltage across them. And generally speaking, any elements in parallel will hold. And you can start looking at bigger circuits that have lots of things in parallel, but if you know what the voltage is across one of those, part of those loops, you know what the voltage is across the other parts of it. And when we define something as being in parallel, they have to share the nodes have to share both endpoints. The nodes are going to be the same on both of those elements. So that defines what's in parallel. So that's if we look at it from the point of view of KCL. So now there's some good math, and we'll walk through it first just on the slide, and then we'll kind of look at it on the paper as well. So the KCL at the top node says that whatever current is running into or coming out of that source is going to split among the two branches, and one's going to run through R1, the other one's going to run through R2. If we apply Ohm's law to that, then we know that the current running through each one of those is going to be the voltage across it divided by the resistance. And KVL told us that those were the same voltage across all of those things. Then the current is the voltage over the resistance, and we sum those up, and that gives us something. We can factor out the voltage in the same way that we factored out the current before, and what we have is 1 over R1 plus 1 over R2 times the voltage. And what that gives us, in the same way that we worked out that we can combine series resistances by just adding all of the values of the resistors up, what we can do with circuits that are in parallel, or at least when we have the resistances in parallel, we can replace all of those resistances with their reciprocals. So, and this is another place where there's a kind of a shortcut given in the book. The equation on the bottom right says Rp equals R1 times R2 over R1 plus R2. And you can remember that if you want, but that particular form of the equation only works for two circuit elements. So I don't use it. I think it's useless. If you use the more general form of the equation, which is on the right, which is not real general at the moment, but if you do it that way, and you say 1 over the total resistance equals 1 over all of the other resistances, you can combine an arbitrary number of resistances in parallel and get a total resistance seen by the circuit. Just don't forget to hit the -1 button on your calculator before you figure out what that final resistance is, or you'll have the reciprocal. You'll be giving me the conductance of the circuit. So, and that's just applying Ohm's law and KVL to these single node pair circuits. So then, how does the current actually divide between those two branches of the circuit? You've heard, perhaps, that current follows the path of least resistance. And that is a folky wisdom kind of thing, but it's actually entirely true. And the equations on the slide get at that. And in this case, what we're going to do when we're trying to figure out how current divides between two different branches, the current, when we're figuring out for a given branch, we're going to put the other resistor on the top of the equation. So we're trying to figure out the current that's running through R1. We put R2 on the top, and we put the sum of the resistances on the bottom. When we're trying to figure out the current running through R2, we put R1 on the top, and we put the sum of the resistances on the bottom. And I'm up here gesturing at the screen with my pen like you can see it. Anyways. So that's, and what will happen then is that the larger that a resistance gets, I wish that I had some more numbers here, but let's just say that we have a 1K resistor and a 3K resistor. Let's say that R1 happens to be 1K, R2 is 3K. So we plug those into this equation. So we have 3K on the top, and then we've got 4K on the bottom. And so the current that's running through the 1K resistor is going to be 3/4 of whatever that original source current was. And that's the smaller of the resistances. The larger of the two resistances gets the leftover 1/4 of the current that's running through it. And so what that tells you is that little saying of the path of least resistance absolutely holds true, that the smaller resistances get the greater amount of the current. as opposed to the larger resistances in a series circuit getting the greater amounts of the voltage across them. So that's how current divides. Let's look at least one example and see where we get here. So this is just a fairly trivial example. We've got a current source, and it's putting out 0.9 milliamps worth of current. And then we've got one resistor over here, which is very clearly in parallel. And then we've got a resistor up top here and a resistor on the side. So as much as anything, what we would like to solve, there's actually going to be three things that we want to solve for. We want to find what is the current, call it I1, that's running through the 60K resistor. There's an I2 that's running through both this 40K resistor and this 80 kilo ohm resistor. And there's also, we're going to call this the voltage across this V0, and we want to know what that is too. So in what we can do is, unfortunately, this doesn't hold with our really nice version of our current division equations, right? Because there's two resistors over here. These two are in series, but the series combination is in parallel with that. So we can reduce this down to a single circuit and then just draw it really quickly. That is two resistances. We've got the 0.9 milliamps here. We've got 60 kilo ohms here, and then we've got the combination. We can just add those up in series. That's 120 kilo ohms there. So now we can do our simple current division equations and find out what at least I1 and I2 are. So let's go ahead and do that. I1 is going to be given as, it's going to be some fraction of the 0.9 milliamps to start with, and the fraction is going to be, we're looking at, this is our R1, so we're going to put R2 on the top, 120 kilo ohms, over the sum of the two resistances, 180 kilo ohms. Smaller resistance is going to get a larger chunk of the current that's running through it, 12 over 18. Times 0.9 e negative 3 is 0.6 milliamps. I2 is going to be, well, do we need to actually write out the current division equation for this? No, because we can use KCL at this point to figure out the other one. If I1 equals 0.6 milliamps and there's 0.9 milliamps rolling in, well, I2 better equal 0.3 milliamps. That's what KCL should tell us. You should get the same answer if you go ahead and you stick in the numbers, and you can work this out on your own, but 0.9 with, let's see, 60 over 180. That should give you 0.3 milliamps as well, but what difference does it make? The point is, I guess the point there is, make sure you use the easiest way to solve these problems and don't just blindly apply the formulas. The last thing that we wanted to figure out is what the voltage is across the 80K resistor, and that's just going to be the V80K is going to equal the current that's running through it, that happens to be I2, times the resistance of 80 kilo ohms. We figured out I2 was 0.3 milliamps. Multiply that by the 80 kilo ohms. 80 E3 times 0.3 E negative 3. And there's 24 volts across that. So you could, if you were interested, you could say, well, it's important to note that the 24 volts that are across this is not going to be the same 24 volts that are across each of these two devices, because this is only part of what's in parallel with the 60K resistor and the 0.9 milliamp source. If you want to know what the voltage is across, in general, what the voltage is across the branches, you need to use these two resistances. And for example, we know that there's 60K across this one with I1 running through it. 60K times 0.6 milliamps gives us 36 volts total. So that's what's across each one of the branches as a whole, or at least across the branch with the current source and the branch with the 60K resistor. And what you should find if you do a voltage divider, and we know that there's 36 volts across this branch, we should find that V0 equals, there's 36 volts across both of those elements, times the one that we're interested in, 80 over 120. And that should still work out to be 24 volts. It should. So that's just kind of extra. That's if you wanted to know what the actual voltage is across each one of those branches and so on. So I think I've got an example. Where did all my examples go for you guys to do? Anyways, let's just move on. For what it's worth, you can also combine current sources in parallel as long as there's nothing else in that branch with the current source. You can push them together in the same way that you push voltage sources together, and you pay attention to the direction of the current. So it works out the same way. I don't want to spend a lot of time on that because it's pretty straightforward. Here's the example that we can do, and I want to get you guys to look at. So this one I want you guys to do. So there's a couple of things for you to look at. Here's a current source. We've got a parallel resistor here. We've got a parallel resistor here. We've got another current source here, and a third resistor here. This is a 6 milliamp source. This is a 4 milliamp source. This is a 4K resistor. This is a 6K resistor. This is a 12K resistor. So I'll do the first step for you, and then I want you to figure out what's going on. The first step is that to get this into a form that we like, we need to get it down to a single current source. And what we need to do is algebraically combine these two current sources. The important thing here is to remember the direction of the currents. The 6 milliamp is going down, the 4 milliamp is going up. So what that's going to leave us with is one of those has to be negative, whichever way you want to think about it, but they're opposing each other. So we're going to end up with a 2 milliamp source in the end. And because the greater one is pointing down, you're going to end up with that one pointing down as well. That should be, I think, fairly intuitive. And regardless of which way you want to think about it, whether you want to call that the negative 6 milliamps because it's not going clockwise, or if you want to call it the positive and call that the negative, either way, they're opposing each other, and so the result is going to be somewhat less than before. It's like having two voltage sources with opposite polarities sitting next to each other. So now you're down to, this is still a single node pair circuit with a 4K, a 6K, and a 12K resistor in it. And what we want to find is what is the power in the 6K resistor. So use current division, use combining resistors in parallel, and find out what what the power is that's being dissipated in the 6K resistor. Yeah?
I'm just confused about the current. Like, if it's going clockwise, or counterclockwise, wouldn't they be going the same direction?
that I don't think so, and I didn't bring the book with me, but that they are more or less opposing each other, and I think that, is that right? Yeah, yeah. It does seem a little counterintuitive, but that is the way that we do it because they are essentially. It does seem like they are kind of feeding each other, but from the point of view of having them in parallel, this one is going down, that one's going up, and so combining them in terms of, I guess what you need to think about is writing essentially like the KCL, right? This current is leaving that node. This current is entering that node. And our convention was when current is entering the node, we give it a negative sign. When it's leaving, we give it a positive sign. And so that's how it ends up combining to give us just a 2 milliamp current source. Okay, so let's try to get this one done real quick. Got one more example I'd like to try to get through. So I did the next step, which is you can do as much or as little of this as you want to, but let's just try to get it down to a form where we have an equation that we can work with it. And that's if we get it down to just two resistors, we can do a current division. Now, just because the 6K resistor is in between the 4K and the 12K resistor doesn't mean that the 4K and the 12K aren't still in parallel with each other. They share the same end nodes, and so therefore they are the same. They are still in parallel. So we can combine those in parallel, combine them reciprocally, 1 over 4K plus 1 over 12K, flip that, that gives you 3K, and that's your parallel combined resistance. And so now we can do a current divider to find out what the current is that is, call that one I1, that's running through the 6K resistor. In this case, well, let's go ahead and just change the direction so we don't have to muck around with negative signs and stuff. But we've got 2 milliamps of current coming in, and we want to put the other resistance on the top of our fraction, 3K over sum, which is 9K. So whatever a third is of 2, or 2/3. So 2/3 of a milliamp is what's running through there. And the power would be 2/3 of a milliamp squared times the resistance of 6K. So 2 divided by 3, e negative 3 times itself times 6,000. That's 2, so that's equals 2.66 repeating milliwatts, I think, as long as I didn't plug something wrong into the calculator. Make sense what we did? All right, so let's look at one last example. We've already kind of dealt with how we combine resistors. In general, we combine series resistors and we just sum up all the resistances from I equals 1 to n of the various individual resistances. That gives us our series resistance. 1 over our parallel resistance is the sum from 1 to n of 1 over all of the constituent resistances. And again, I guess practically speaking, what this tells us is that when you add resistors in series, the overall resistance goes up. Whereas when you combine resistors in parallel, the overall resistance goes down. So let's look at, got one example that I want to try to do, and I think I'm going to have enough time to do it. This is just a big network of resistors, and we want to see what is the overall resistance that's seen looking in at the terminals, call them A and B. What is the equivalent resistance, RAB? And this is a very heavily contrived problem. I don't know when you'd ever see anything like this in real life, but we will see things that are not entirely dissimilar to it going forward in other aspects of the class. Okay, so all the ones across the top are 2K resistors, 2K. This is a 10K resistor. This one here is 4K. This is 9K, 6K, 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 1K, and 2Ks. Yeah. So that's our ridiculous resistor network, and we want to find the equivalent resistance looking in at the terminals A and B. And so we know we need to make sure that we're doing appropriately is that we're finding the resistors that are in parallel and are in series with each other and reducing it appropriately. So the first thing and you're always going to start at the far end of the from the terminals, start way over on the other side. So whatever, whatever that means, given the circuit layout that you're given. So the 2 and the 1 are in series with each other, and that series combination is in parallel with that 6K resistor because they share the same end nodes, and that's our definition of parallel. So what we've got effectively is we've got a 3K resistor, which is a series combination of the 1 and the 2, and we've got a 6K resistor in parallel. Their equivalent resistance, call it RP1, is 1 over 3 plus 1 over 6 is 2. So we can change this network. So now we've got 10K. This is our 2K, which is our RP1. This is the 10K. This is a 6K. This is a 2K, 6K, 9K, 4K, 2K. So one of probably the hardest thing and the thing that might be the most confusing is how this particular resistor ended up on the far side over here. It's just important to remember that the 10K here is in series with all of this junk. And we reduce these two series, this parallel, and this extra little corner in the circuit doesn't necessarily need to exist aside from making it kind of look regular and pretty. If we got rid of that and we kind of pushed it at an angle so that but it would still connect at the same place. And so the 2K resistor still belongs over here. Obviously the 10K and the 2K are in parallel with each other, or they're in series with each other and in parallel with the 6K, so we have 1 over 12 plus 1 over 6 equals 1 over RP2. 1 over 12 plus 1 over 6. And that gives us 4. So this reduces again. 4K. We got 2K. We've got, this is our RP2 of 4K. We've got the 6K resistor here. So, and the 9K here. And 6K, 2K, 4K, 2K. Again, 2K and 4K are in series, so we've got 6K in parallel with this 6K. And 1 over 6 plus 1 over 6. We can reduce that. That's a 3K resistor. So now we've got 2K. This is the 4K resistor. We've got, this was 3. This is 3K, which is these two in series in parallel with this one. We've got 9K here. We've got 4K here. We've got 2K here. The 3 and the 9 are in series in parallel with the 4. So we got 1 over 12 plus 1 over 4, which gives us 3. And so this reduces then down to a 2K resistor, and just the single resistance. This was the 3K. This was the 2K. The 3K comes as the series. This is the 12K in parallel with the 4K. And then you add those up. Overall resistance is 5 kilo ohms, equals the equivalent resistance from RAB. So that should give you enough to at least get started on most of the homework. Take a look at it. We'll do some more examples of this and start moving into maybe a little bit into Chapter 3. The quiz tomorrow would look at some of the current division, voltage division, and resistor combination. So take a look at that. If you have any questions, let me know. Otherwise, we'll see you tomorrow. Have a good one.